Okay, we welcome all participants to this second webinar in the webinar series of the Applied Artificial Intelligence and Robotics Research Lab of the Obafemi Awolowo University Department of Electronic and Electrical Engineering. Today we'll be having a speaker, Dr. A.N. Jubril, who's a control and instrumentation specialist. Dr. Jubril works on systems, he works on modeling systems with high dimensional data and non-linearities, and usually focusing on optimization problems. Today, Dr. Jubril will be discussing a set of techniques that have experienced a resurgence in the last 10 years. And I trust that he'll be able to show that these techniques can be very useful in research areas spanning the entire science and engineering spectrum, not just control engineering. I should mention the goal of the Air Lab seminar webinar series is to stimulate high quality research in Nigeria by collapsing distance between experts abroad and in Nigeria. And so we aim to have high quality discussions between scholars both here and abroad. And we are very happy to have Dr. Jubril with us today. Thank you, Dr. Jubril. I cede the floor to you. Thank you.
Thank you very much, sir.
Thank you very much.
Yeah, thank you for having me to present this seminar. Just like you have rightly said, there's so much that is happening in the world of nonlinear systems. And I believe you are seeing my screen.
Oh, not yet. Your screen is not showing.
Okay.
Then, Dr. Jubril, is it possible to increase your volume a bit?
Okay, I'll do that, sir. I'll do that. Well, first thing is my screen. Are you seeing my screen? Not yet. Sorry, let me just share my screen. Yeah.
Yes, we can see it now.
Okay, thank you very much, sir. Just like the title reads, Modal Description of Nonlinear Dynamical System with Koopman Operator Theory. Okay, now I'll start by saying that everything we as scientists and engineers, what we are trying to do is to try to understand nature. And nature, we have so many processes in nature that are very complex to understand. And if science, all that we are doing in science is just trying to understand this. And we do a lot of measurements, trying to see how those things can be summarized in a physical law. And that's basically what we do in science. So most complex system or most complex processes in the world or that we try to understand can be modeled as dynamical system, because you have evolution of those things with time, of those variables. Let's say, for example, the temperature of a particular place. The temperature of a particular place at a particular location evolves with time. I mean, it changes with time. Or maybe the pressure of a particular place, or maybe the signal in our brains. All those things can be considered as a dynamical system, because we have evolution of those parameters, of those variables with time. Just like I've said. Okay. I don't know if so people are making some. Okay. Such complex system includes the power grid. We have a very complex power grid. We have the human neural net. Then we also have other very complex systems or processes in biology, and some of them in epidemiology and so on. But such complexes, we can consider them, as I've said, as a dynamical system. So when we are talking about dynamical system, you can look at that dynamical system as a system. And this time it has inputs and also it has outputs. So mathematically, you can represent it as a differential equation, just like you see here, a differential equation, which sometimes can we may not have access to, or rather, can I say we don't have access, we may not have access to those states. So here we define the input of the system, the states which are usually hidden, that is not usually exposed. Then we also have the output of the system, which is represented by Y. So the dynamics of the system is written as the derivative of this differential equation, which is usually written in form of state space. So this we have a differential equation x dot equals to f, which is dependent on the state, which is usually hidden, and also the input. And then the output that we have access to is a function of the state within and also the input. Now, we must note that most real physical systems are nonlinear. They are nonlinear functions. I mean, they are nonlinear. It's not just, it doesn't obey the principle of superposition. They are very difficult to represent sometimes, or they are represented by very complex functions. So F here, which are functions of X and U, the input and the space, and G, which is the output equation, they are both nonlinear. Now, when the observer, like I said, we want to understand nature. I want to summarize it in form of a law or a model. We want to put a model on a particular process. A process is happening, maybe we want to understand the growth or the growth of infection in a particular place. So we are taking measurements at every time. We are taking measurement of the people, for example, the COVID infection. Now we are taking measurement of the people who are infected and at different locations. So those are measurements that we can, but the real cause, we don't have access to the real cause. The things that are happening within the body, we don't have access to them. So the observer may not, and sometimes, many a time, do not have direct influence over what is causing it or what can control it. So our system then, that we consider the input. We consider the, or we can say the system now reduces to what we call a time series, because you only have access to the number of people who are infected with the disease or with the virus. So it's just a process generating data, and you have the data, but you don't have access to the cause, or to maybe you don't even have access to control what is happening. So the system becomes a time series process or data. Time series. Now the system input is considered. Now, when you don't have access to the input or what is controlling that data generating process, then you might as well consider the input U as one of the variables that you want to, that you are actually measuring. So in general, we can now look at the system as a data generating process, which is just generating a Y, and the governing equation, the dynamics of the system, is not known to us. So most of the sciences, most of the things we have is just based on this. Actually, this is hidden from us. We don't have access to this, but this is the measurements we take. Like I said the other time, measurement of the people, measuring the people who are infected with COVID in a particular environment. So this that is generating it becomes something we want to know, so that we can find a way of controlling the process or the system. Now, why are we trying to? Why is it a problem? Or why are we considering the Koopman that we are trying to talk about? Now, one thing we have observed is that if a system is linear, then the system can be completely characterized by spectral decomposition. For us, if you have, generally normally write a linear system as a system Y equals to AX. So that means we have the Y is the output, the input is X, and then you have a matrix operator operating on the input X to give you the output Y. So in that case, we can actually characterize. It has been known. It's a very well-known it's a well-known knowledge that you can completely characterize every linear system by spectral characteristics. So, I mean, we have the Eugen values and the Eugen vector. Another important thing with linear system is the simplicity of analysis. As I've said the other time, the simplicity is based on what we call the superposition theorem. So that means if a system is linear, then superposition holds. Another thing is people, because of the homogeneity and the simplicity of analysis of linear system, it has reached a mature state and is well understood, and it's very easy to deploy it in application. But the problem with nonlinear is that for every nonlinear system, you need a specific method. There's no general, like we have for linear system analysis. You don't have a general method for all nonlinear systems. And another thing is that you do not always guarantee closed loop a global solution, and it's very difficult to analyze, especially when you have disturbances and uncertainty. So most efforts now becomes, when you are analyzing nonlinear system or nonlinear dynamical system, or when you have time series, as I've said, in general, most data generating process in nature, they are nonlinear. So we want to see how we can use this matured and well understood linear analysis method in analyzing nonlinear complex processes in the world. So now Koopman's operator theory. Now in about 1931, Koopman, along with some people, are working on ergodic theory. He introduced an operator theoretic perspective of dynamical system. As I've said, a dynamical system is just something that is evolving. You have a set of variables that is evolving with time. It's anything that is changing with time. You have those variables changing with time. So you can consider that as dynamical system. So he introduced operator theoretic perspective of dynamical system. So in this case, just like we have in analysis of linear system, we have for every linear system, we have these functions, or what we call Eugen functions or basis functions for linear systems. And we have these complex exponential functions. They are Eugen functions of all linear systems. So in a way, you can actually, if you have a system, you can decompose them into linear combination of different complex exponential functions. So with this, people are looking for different basis functions that can help to express or to capture the information in every signal. So this was proposed. The Koopman's operator theoretic perspective of dynamical system was proposed in 1931. And then this proposes a nonlinear lifting of the observable. I'll still make all this clear later. So for Hamiltonian system, this is energy system, into a space where its time evolution is linear. Note what I've said. Use a nonlinear lifting of the system of the variables into another domain, where the system can be expressed as a linear function or a linear process. And that is the selling point of the Koopman's operator theory. As I've said, the linear analysis method has been well understood and has reached a stage of maturity. But for nonlinear system, you have a lot of problems, as I've said. So this is helping to convert a nonlinear system into a linear system. Now, this was generalized. Now, this was generalized to continuous spectrum by Koopman along with Newman, and that was in 1932. But they renewed for about from 1932, 1931 till now. Not much has been had on this theory, Koopman operator theory, until 2005, when Mesick was able to renew interest on the theory, and also provide a computational way of actually approximating the Koopman's operator. Okay, now let's look at basic dynamical system. Now consider the time series dynamical system, which is written by this as a differential equation x dot equals to f of x. Now x is the state of the vector on a finite dimensional manifold. I mean, this is on a particular set of equations that defines where x can be found. Now, for any t, now you can easily solve this because it's a first order differential equation. You can easily solve this and say x, you can solve this by saying x equals to integral of f of x dt. I mean, just by looking at this. Now, for every given t, you can consider the flow. Now, that means we want to find x at any time in terms of initial value. So for a given time t, you can consider what we call the flow map. That is what operates on a state and then gives the next state. That's called that function that transition operator that takes a particular initial state and push it to the next state. So if you are looking at a given time t, you can consider the flow map f of t that maps it from one of the states in M. In M is a manifold that is defined by a set of equations. So then pushes it into M, move it to a particular point in M. Now, that means it push forward x naught at t naught, pushes forward in time into another state x at t naught plus t, such that we have this equation. Now, this is like I said, the flow map, and it gives us the next value given this time t. So we can write the flow map as this. So it operates on x of t naught and move it to x of t naught plus t. So the flow map satisfies some properties. So that means if you apply f of s on x naught, it moves it to x of x t naught plus s. Yeah. Then if you apply this on the result of this, it also moves it to f of it's the same thing as applying it the same time. Applying it okay, let me put it this way. Applying f of s on x naught, we push it to f of x naught or x at t naught plus s. Now, when you apply the second another time, you apply f of t on the result of that, you get this. So what we are looking at is that actually this t, this composition can be taken as a single operation. So that means if you apply this first time and then this next time, it can be considered as applying it just once, given that s and t are greater than 0. So since most of the time we have discrete values when we take measurement, so that means those measurements are actually in form of sequences. So we can look at discrete time dynamical system such that we can look, instead of writing this or writing this for continuous time system, from now on we'll consider the discrete time dynamical system. So for SK, what we mean by SK here is x at, because we have discretized the time, is as x at tk, or in other way, we can look at it as this, where this is the change, the sampling, where delta t is the sampling time, or t here as the sampling time. So we write SK as this, and F is the flow map. So instead of considering this from now, we look at this, which is a discrete time dynamical system. Now, Koopman's operator theory. What Koopman operator theory does is it's an operator that advances the measurements from when you apply K, Koopman's on a particular state, it advances that state to another state. I mean, forward in time. It kind of push it forward in time. So it advances the state of the dynamical system with the flow of f of x. Now, what are we saying here? Now, we have access, like I said the other time, most of the time we don't have access to the state, the governing dynamics of the system. Well, we have access to some measurement about the state, which we call the output. Why? Now, so Koopman operator advances measurement function. Let's say we have a system, the system we considered the other time. Okay, this system, we have x of this, but we don't have access to this. But this particular function is this equation is the governing function. But we have access to this. We can take measurements, which is y equals to gx. Now, what Koopman's theory was able to do was like, always we found that is that this operator, when it operates on g of x, which we have access to, because we have been able to take measurement g of x. Now, K or the Koopman's operator advances g of x to g of x plus 1. I mean, x of t plus 1. So it advances the states. And so it gives the measurement of the state at x t plus 1. I hope I'm making, okay. So considering the flow map, let's say the flow map is applied t times. It advances the state from this forward along the trajectory by time t. So x of t equals to this. Now, the Koopman's operator K actually maps this in what we call the function space. Now, can I also remind us that now this is a state, x is a state, but this is the output. Now, this output is residing in another space, which we call the function space, or the measurable space. I mean, that's the measurement space. This is state space, but this is another function space. So this g of x, calligraphic g of x, is actually the output, the measurement space. Measurement space. So Koopmans operate on the measurement and then push forward the advances, the measurements, the y output by, advances the state of the output of the output. So to define that, let's look at this. So let's say you have a Koopman's operator indexed by t operating on g of x. Now, what this does is it gives the output of the state forwarded, advanced by t already. So it's like when you apply t times, it's actually give you the output that has been advanced by t time. So g of x being a set of measurements is a space of set of measurement, or what we call the observable function. Like I've said the other time, these are the variables of measurement that are observable, that the observer have access to. Also, and usually is of higher dimension than the state space x. The x is the state space. So g takes each of the g function, each of the measurements observable function takes the state to a complex function space, and this is a scalar. I mean, we are looking at each g as a scalar function. So it takes x as a state variable and maps it to as a scalar value, gives us a measurement. Or in another form, we can say g of t is Koopman's operating on G, indexed by T. Okay, now as I was saying the other time, that the most important thing most important thing when we want to do analysis is linearity. I mean, when linearity makes the analysis to be easier to handle. So the most important property of the Koopman's operator is its linearity over the observable space, or what we call over G of X, which is the observable space. Now you find out that if you have a linear combination of functions, let's say we have alpha 1 G1 plus alpha 2 G2, where G1 and G2 are measurement functions, or they are form of observable functions of the states. Now, if you apply K, the Koopman's operator on this, it gives us this. It gives us this, and that means it becomes a linear combination of the linear combination of Koopman's operated the observable functions. So it's like the linearity of Koopman's operator on G of X can be seen here. So we can say that the Koopman's operator is linear on the observable function space. So KT here is linear despite the non-linearity of this. Like we said the other time, this is the flow map of the non-linear dynamical system. So the Koopman's operator is linear despite the non-linearity of the dynamical system. And now the caveat here is that although it's giving us a linear, can represent the system as a linear system, but this time it's trading finite dimensionality of X for an infinite dimensionality in G of X. That's the observable space. Now, and this we can see, this becomes the Achilles tendon of this Koopman's operator. That although yes, it can transform a nonlinear problem, a nonlinear system, a nonlinear dynamical problem, can transform that to a linear system or linear process. But this time it gives an infinite dimensionality in that domain where it can be represented by it's a linear system. So for this to be usable, for we want to be able to make use of this, because with the infinite dimensionality, that is, if you have to represent anything by infinite numbers of functions, then that means it's not really computationally possible. So that means we have to find a way to resolve that infinite dimensionality of the Koopman's operator. So agent function decomposition of Koopman's operator. Now, let's look at the composition of Koopman's operator. You know, for linear systems, for general linear systems, you can do what's called agent decomposition of a matrix. A matrix can be decomposed into its eigenvectors and eigenvalues. Now, the same thing can be done for the space, the Koopman's operator. Now, the space of observable function G of S is defined or spanned by set of eigenfunctions, just like we have in Fourier domain. Every point in the domain is spanned by a set of infinite number of complex exponential functions. So the same thing here too. Just like Fourier, this is also, it has an infinite number of eigenfunctions, which we call phi i's. This span the observable function space. So And these functions, like you said, is an agent function. So that means if Koopman operate on each of these agent functions, what it translates to is it gives us the function back, or let's say it scales the function. So in the same direction. So applying Koopmans on this. So please, let's assume that this T is not there. Now Koopman's operating on this gives us this back, but in a form of scaled version. So any function in this direction is scaled by a value called Eugen value. So lambda I being the corresponding Eugen values of the Eugen function base. So that makes it very easy to handle. The state space of X is now mapped into GS by G of X. Every observable function G of X can now be represented if G of X is mapped to that of observable. If every X is lifted and mapped using G of X into the observable space, it can be represented as a linear combination of all the Eugen functions. Like said the other time, just like we have basis vectors in the three-dimensional space, every point in the three-dimensional space can be written as a linear combination of those unit vectors that span or that defines that vector space. So the same thing here, this G of X now is written as a linear combination of those Eugen functions of that observable space, G of X. So you see, you can write any function in that observable space as a linear combination like this. And so if we apply, given this expansion or decomposition, given this decomposition in the observable space, applying Koopman on any function in that observable space can be written as this. That is applying K on this expression here. Now, this is just the coefficient. This is the coefficient, and this is the Eugen function. And we have said, using this, that when Koopmans operate on this, it scales this by its Eugen value. So this becomes this. So it's still spanned. So this is like just span, it's still in the same space. So that's one good thing. And this allows us to be able to analyze Koopman's, or to decompose any function in the Koopman's domain as a set of this. And now this becomes what is now important. Just like in Fourier, if you take a signal in Fourier and then you decompose it in Fourier, the coefficients of those complex exponential functions becomes the Fourier coefficient. And now those are the things that we look for, and those are the one that defines, defines the signal, because we know these are always there. So these ones are what we call the Koopman's mode. The Koopman's mode. This is the Koopman Eugen value. This is the Koopman Eugen function, and this is the Koopman mode for this signal. For every signal G of S, this is unique. This is different. You can have, this is all these one, all the 5 Ks are always there. But this one, given G of X, this is the one that defines G of X. So we can see this as the features. The features we'll be looking for every signal. Now, you can look at this as a feature that defines this particular signal. So applying this does not, we find out that, yes, it's multiplied by this, but this particular feature is unique. It's not changing. Even after applying Koopman's on G of X n times or k times or p times. Now, in practice, like I said, we want to look at discrete sample data. So therefore, as I've said, we are only considering discrete time systems like x k plus 1 equals to f of where f is the flow map. So we have said it that if Koopman operate on any observable function, which is in G calligraphy of X, which is in the observable function, it gives us this. It gives us at least the push forward value of the measured function at the next state. And so we see that this is a simple evolution under Koopman's operator. Now, like I said the other time, so Koopman operating on any one of them, or on each of the Eugen function, operating on this gives us this, and this is the same thing as this phi f of k plus 1. So Koopman operating on each of the Eugen function actually move it a step, to the future, and advances it by one time unit. So Koopman's mode decomposition and finite representation. As I've said, the dimension of the observable space, the calligraphy G, like we talked about the other time, is infinite. Like I say, that makes this the method actually intractable, because we cannot deal with infinite dimensional space. So let's consider a measurement. Let's just take G1, G2, measurement of a particular dynamical system. So we take different measurements. We take different sets of measurement. Let's say, for example, a person walking and want to look at or analyze the gait of human being. Now we can measure. Let's say G1 is the position of the ankle, then G2 is the position of the knee, G3 is the position of the elbow, G4 is like that. So for a particular person, we can take different measurements of that process. Now we express each element in the basis of the Eugen function. So that means each of these functions can now be decomposed. Each of these functions can be decomposed into the basis function, basis of the Eugen function of the function space. So each of these can be represented. So this actually now is a vector. This is a vector. So alpha k, this is supposed to be vector of measurement. So alpha k is a vector coefficient called the Kates-Koopman's mode, corresponding to phi k. The dynamics of the measurement can now be expressed as this. Now I've written this the other time. So if you apply it 80 times, then it's going to have phi k raised to power t. And this, as I've said, is the Koopman's mode, and is unique. It's like the feature that defines the measurement g of x. And this, we can look at the feature that we can use in analysis or in analyzing the system, and can be used in classification in regression too. Okay. Okay. I think I'll talk about this. Now, invariant Eugen spaces and finite dimensional model. Now, for the Koopman analysis to be usable, then that means we have to approximate the Koopman's operator. So to apply it, we have to approximate the evolution of the invariant subspace. What I'm saying here is, now the space G of X, not indexed by P. The former one is infinite dimensional, and so what we are doing here is to approximate it. So we look for, in the infinite dimensional space, we look for a subspace, where we can approximate the operation, and which is spanned by a set of Eugen function. So now we are not going to look at the infinite number of Eugen function. We are going to look at only p number of them in that subspace. That subspace is going to look at only p number of the phi k, the Eugen function of the of the function space g of x. Now, so that means it's just going to be an approximation. It's not going to actually capture the full thing. So that means we are going to lose some information. So the Koopman invariant subspace, we are going to look at a particular subspace in that Koopman function space, and see the ones that actually, the process actually can be captured. There are possible, there are sometimes that we have a particular process not being represented by the infinite number of Eugen function, but they are it's residing in a particular subspace of the larger space, the infinite dimensional space GP, G of X. So a Koopman invariant subspace is defined by the span of this P number of the Eugen functions, where you have G equals to this. So now we are only picking P number of the infinite dimension. You have the infinite dimensional space. So out of this infinite number of phi k, we are taking only P numbers. So, and we know that whenever Koopman operate on any one of this, it resides, it's invariant. So we are looking at a particular finite dimensional approximation. So that means we are going to project everything, the problem onto a smaller part of the Koopman function space, or G of X, which we now call GP, which is an invariant subspace. Subspace of the larger infinite dimensional G of X. So we have G of X now, which is an approximation, taking only P of those Eugen functions. And when acted upon, like we said the other time, it still remains in the subspace. And that's why it's called an invariant subspace. So when Koopman operates on G, on any of those measurements that are defined within this space, it still remains in this space. So the approximation reduces to determining those Eugen functions that will capture G very well. So although we have infinite dimensional, now we need to select some phi k's that are invariant to the operation of k, and still captures our measurement space that we have. Okay, now let's look at an example of Koopman linearization. Now consider an example of a single fixed point system from A2IR2 et al. 2014. Now this is a nonlinear system because we have here we have a power greater than 1 here. So this makes the problem nonlinear. But this also have another thing is that this is just a single fixed point. You set this to 0, you have x equals to 0, and you set this to 0, you have everything here equals to 0, and then we have x2 equals to x1 squared, and that defines the manifold on which this is. Now we can, by Koopman's linearization approach, what we want to do here is to lift this part. This is two-dimensional system. The system dimension of the system is 2. You have x1 and x2. Now we want to move this, lift this up, and embed it in another space, higher dimensional space. So we want to do we want to add a measurement. We want to augment the states by nonlinear measurements g equals to s squared. Sorry, it's supposed to be g equals to x1 squared, so that we now have an augmented space or augmented state having x1, x2 of this old space, and then we have this new added state or state variable. So we have now this is in two-dimensional space, but now we have by this measurement g equals to x1 squared. We are now trying to embed the system in this new space. Now with an invariant manifold. Now this is an equation that also on which this equation or the manifold on which this applying Koopman will make it invariant. Okay, so let's say we have this. We can rewrite this. We can write this as x1 equals to y1, x2 equals to y2, or y2 equals to x2, and then y3 is now equals to this, equals to g equals to y1 squared. Yeah, equals to y1 squared. Now, if we, after some little calculations, or we can rewrite this as this. We can rewrite this as this. Now, this becomes a linear problem because these are constants. These are constant, and these are the variables. So you can write this as y dot equals to a cap. Let's say this particular matrix times this. So by lifting, by nonlinear measurements, or lifting that space of measurement into higher dimensional space or measure space, now we have converted a nonlinear problem, a nonlinear system, as this, as a linear problem. Now, but the problem is this. Now, let's assume this problem is not this, and we just say, let's this nonlinearity be on, let's say the nonlinearity is on x2. Now, if we change, let's say this is f1 of x1, x2, and this is f2. Now, if f2 equals to this, you observe that the closure problem sets in. Now, what do you mean by closure problem? If I differentiate, the other time, if we differentiate this is x1. If I differentiate x1, if I differentiate this, I'm going to have 2x1 dot. And 2x1 dot becomes, because x1 dot is equals to this, just becomes 2 alpha x1 squared. And we know x1 squared is y3. And that means you can easily solve this. I mean, that's how you got this. But now, when you have f2 equals to this, compare this. You're just swapping the power of x1 and x2 in this place. Now, if you do this, we generate new variables. And for every differentiation, we continue to generate new sets of variables. And that brings us to what's called the closure problem. So for that kind of, for this kind of system, you find out that it cannot actually be embedded in the three-dimensional subspace. But this requires an infinite dimensional subspace. Now, this is typical of what's called the Kalman linearization, which also, about the same time with Koopman, came up with using polynomial Eugen functions. Like Koopman generalized the whole thing, but Kalman says that let's try a polynomial Eugen function phi k, and we observe that this problem, this is a problem of Kalman linearization, and that's the problem of closure. Closure, that means if you try to introduce, you augment the space, you find out that you continue to augment it until you get to infinity. So this kind of problem, cannot be solved by, cannot actually be embedded in a finite dimensional subspace, and therefore it needs an infinite. You have to do truncation at a particular point. While this one does not need truncation, this particular one does not need truncation by doing this. So that's general way of doing Koopman's linearization. But like I've said, because of the closure problem, we have to look for, select, like I said here, the problem is determining the Eugen function coordinates, phi k. Now, if you are not careful, it's possible to have a problem, what's called the closure problem. Okay, now data-driven approaches to computing agent characteristics of Koopman operator. Now, we have showed that it is possible to embed a nonlinear problem and reduce that nonlinear problem into a linear problem like this. And now this linear problem, we have a matured, a set of two to solve and analyze this kind of problem. We have, there are, a lot of tools to solve this kind of problem. But how do we know which phi k to select? How do we know this which phi k to select? And that's there are different approximations to Koopman's operator. There are so many different operations. So various methods have been proposed and implemented to compute finite dimensional approximates of the Koopman's operator. Now, the most common one is this what we call dynamic mode decomposition. That's a very common one. We also have what's called the generalized Laplace analysis. Is also by Mesick. Then we also have Prony approximation by Mesick too and Suzuki. But dynamic mode, what's called DMD, called DMD, has gained more popularization because of its simplicity. So we are going to look at that approximation using DMD. Now, DMD is dynamic mode decomposition. Originally was introduced in Schmid in the fluid dynamic community, and was originally developed to identify temporal and coherent structures. Now, what do you mean by, why do we talk about this? Now, if you are using for dynamic if you want to do decomposition using Fourier, one thing we know is that Fourier will be good for time domain analysis. For temporal analysis. But if you want to do very good spatial, although Fourier is also used for spatial decomposition and analysis, but generally spatial and temporal, it cannot handle the two at the same time. So the spatial decomposition analysis is well handled by this signal value decomposition. So DMD now combines the strength of both algorithms. So it uses SVD for spatial analysis and decomposition, and also capturing of spatial information, and also temporal uses a Fourier transform for time information. So the DMD is now considered as a combination of both SVD and the Fourier transform. So DMD also approximates the Koopman's operator restricted to the measurement space of the state of the system. So, and another thing is that it's a very simple formulation in linear algebra. It's very easy to understand. Now, using DMD, we are going to use DMD to approximate Koopman's operator. The algorithm seeks a best linear operator that approximates the Koopman operator K. As I've said, restricted to the measurement space spanned by the measurement of X, although G1, G2, G3 to GP. So let's say we have a system of XK equals to AXK. DMD assumes you have access to the states. It assumes we have access to the state. So DMD, being a data-driven, relies on collection of snapshot. That means taking measurement at time tk. So, and as I've said, it assumes we have access to the full state of the system. So each snapshot, that is the measurement of the state at tk, at time tk, is a group of measurement at tk, and a snapshot at time, x prime at tk is another snapshot taking one time step tk plus 1 in the future. So it's like, this is a one-time step. This is like an advanced, a time advanced version of X. So let's say we arrange the matrices into we arrange the matrices into two sets of two matrices X and X prime. Now X, we have matrices of time, the one taken at time at different times, and X prime would be X shifted by one time step. So X prime is X shifted by one time step. I hope you get that. Okay. Now, relationship between Koopmans and DMD. Like I said, let's say we have a manifold on which X is residing. Let's say this is a space where X is moving. So if this is the flow map, if we start at point X1 and then you FT, the flow map operates on X1, it will move it to X2. If FT operates on X2, it will move it to X3, and so on until you get to Xn. Now, if we take measurements, let's say we do a lifting, we take a measurement of the state. So we take measurement of X1. Let's at X1 using G. G of X1 becomes Y1. G of X2 becomes Y2. G of X3 becomes Y3, and so on like that until you get to Yn. Now, this particular flow map is non-linear, like we said the other time. This particular flow map is non-linear, but by moving it, by mapping this particular space, by this particular, this particular orbit, this particular space here, into another space. In this space, we have Y2 equals to KT times Y1. And actually, this is a linear space. This is a linear space. So this is easily explained by saying X1 is lifted to Y1 by G. Then for each application of the Koopman's operator on Y1 moves it a time step ahead, a time step ahead, a time step until you get to this point. So basically, that is relationship between. So you can say Koopman works on the observable space, but DMD operates is an operation, or is like approximation of f of t in the state space. DMD approximates f of t in the state space. So we believe, everything that is done is actually here. DMD operates here, but Koopman operates here. Koopman operates in the observable space. Okay. Now, like I said the other time, to apply DMD, to use DMD, we need two set of matrices. Matrices X and X prime. So matrices X1 is a set of measurements. Let's say X at X1, X2, X3 at T1, and then at another point T2, a time step after T1, we have T2. So those measurements of states are also as a column vector stacked along with this, and then we have that until we have the measurements of the state at Tm. Then we only need to shift this. We only need to shift this by one measurement step, or a one-time step. So we shift X2 to this here. We shift X3 to, X at T3 to this, and then there is one we do not have, and that's X at Tm plus 1. So that we now, the two now become the same. We now have the same number of columns in both X and X prime. So we now write this, because we know that this is a time shifted, a time advanced of x. So x prime is time advance of x. So A here is an approximate, is the DMD approximation of the function f. A here is the approximation of the nonlinear flow map of f. So here we have x prime equals to ax, and this is supposed to be an approximation, not equals to an approximation. Yeah, this is supposed to be an approximation because this is not f. This is not f. So this is just an approximate operator or approximation of f. So this is solved as a least square error or least error fit problem. So that means if you take this, you should have some part here, the residual here. So x prime minus ax should still give us something as error here. So we want to minimize this error over a. We look at over a. So we solve this using we minimize this error. And f here is called the Frobenius norm, and this is solved, and we have x prime times x pseudo inverse. So this actually is the solution of the problem, and this is very simple because this is just take x and x prime, and then you find the pseudo inverse, and then that is all, and that you have an approximate approximation of the nonlinear flow map. Okay, so how do you go about that? Now there are different variants of DMD. This is the way DMD solves this, and now we want to use this to actually find or approximate the Koopman's operator. So let's look at the algorithm. Now, like I said the other time, DMD is going to operate on the DMD actually is designed for the state space. Koopman does approximation. We want to look for Koopman approximation in the function space. So it's like we are now going to use DMD approach on the Koopman on the observable space. That's basically what we are going to do using DMD approach. Now, I also said the other time that the DMD algorithm is basically an SVD plus Fourier algorithm. The two algorithms are combined in DMD. So we want to consider singular value decomposition of x, and that means we have x. You can write x as actually apology for this. It's supposed to be U sigma V conjugate transpose. So here we're supposed to have a star here, U sigma V. And now the matrices U and V. U is n by n and V is m by n, and they are both unitary. So that means they are orthogonal to one another. So if you multiply them by its transpose, you get identity matrix. Okay, so now dealing with matrix A here is it has n square elements and becomes intractable for if they have a very high dimensional data. So what is done is most of the time we look at the SVD and we do model reduction at this point. So let's say if after we have done the singular value decomposition, we look at the singular values with relative values of those singular values, and then we look at the ones that are appreciable and where most of the energy is contained. Then if the rank of x is equals R, Then we can actually approximate this high dimensional data here. You can represent it by UR, sigma R, and VR. Actually, sorry again, it's supposed to have a conjugate transpose. I mean, a star here to show that it's conjugate transpose. Now, projecting A onto the first POD mode. Now, U has the spatial information of X, while V captures the time dynamics of the data. Now, using only using R numbers of U columns, then that means we are projecting A onto the modes of just R number of modes in UR, and then we can also, since we here we assume we can reduce, but that projection you can do this, and because this is U U is unitary, as I've said the other time. U is unitary. We can by this kind of transformation. We are transforming or trying to project A onto the modes of UR. So A, like we have found in the previous slide, is X prime times X pseudo inverse. So we can easily write A as this. A as this. Okay. Now, the eigenvectors of A, are the modes of the DMD modes, which we write as this, where W is the left matrix of the eigenvectors of A. Now, what actually we are doing here is we are trying to rewrite X of T every X. We are writing each of the X's here. We are writing them, or we are decomposing them into the eigen function, then eigen values, and then the coefficient, what we call the DMD modes, or what? Sorry, the Koopman mode. This is the Koopman mode. So here we have written it in form of, these are things that captures the time dynamics, or the frequency content and time dynamics, and this also, they are the spatial information about the signal X of T. Like I said the other time, for this decomposition, or DMD or Koopman decomposition, this is important. The modes, the DMD mode is important, and this also all these ones, I mean, exponential omega JT also tells us about the time dynamics of the data of X of T. Okay, so this is what we call the classical or the standard DMD mode. That's, I mean, this particular one, we can find the DMD approximation using this. And another method is using Ankel DMD. I mean, we have a lot of DMD. So with this one, this is based on Takings embedding theorem, that actually, instead of it was observed by Takings that we can only partial observation by that's partial observation of a system that are time delayed. We can build a coordinate system 5Ks. So so based on this, you can take measurement of a single point. For example, X at T1, at T2, at T3. So this is time delayed time delay measurement of this, like that, until we get to T Q plus P. Now, this can be reshaped such that we have the first row, and then the second row is a shifted form of the first row. Then the next row is the shifted form of the previous row until we get to the last one. taking only P number of the measurements at T time measurement of the measurement of the states. So now this is, using the Ankel DMD, just what we do is just do SVD decomposition of this, and then we take the R numbers of as we said the other time, the columns of U spans captures the spatial information, while the columns of V provides information on time dynamics. So by using this, we can actually rewrite, we can determine the modes, which are U, can determine the time dynamics, the time dynamics of the Eugen values from V, and then from that we can actually write a system dynamics from the Ankel matrix. Now there are also different variations of this. We have row Ankel DMD. We have column Ankel DMD, and so many variants of that. Okay, now that we know how to, we have a Koopman's theory, that is how to lift a particular nonlinear system into a particular space where it is linear, but we said that linear space is infinite dimensional, and then we want to find a finite dimensional approximation in that function space. That's basically what the Koopman's applied Koopman is about. But we also said there are different ways to find the approximation of the Koopman, and basically using the DMD for Koopman. By using this, then we can find the approximate finite dimensional approximation of the Koopman operator. Now, but in dynamical system, like we said the other time, we don't have access to the inputs. In most of the processes, complex processes, we only have measurements of the system. So most of the operation in dynamical system does not include the inputs. But like we have seen, if the input is not known, then maybe we can actually take the input as part of the state, and by doing that, we can actually reduce the problem to normal dynamical problem. So the DMD is a form of system identification, and there's a connection between DMD and Eugen realization algorithm using Ankel, because Ankel is a product of observability Gramian and controllability Gramian. So this algorithm now is based on this model that we have an additional control history. So we take measurement, just like we are taking measurement of the states. We take measurement of the control if we have access to them now. And A and B are now approximated as this. So this is like our A matrix. Is like rewriting this as augmented states of augmented states. So we now have an augmented state of XK UK. So our states now, a new state will now be in terms of XK and UK. So the additional matrix for control history for the control, this, which is this. So we now have A and B approximated from this. So we can write since these are known, we are trying to find this. This is like the new X, and this is a step ahead or shifted version of X. So we can use this. Okay, So we can do system identification still using DMD, and also we can also consider what you call the extended DMD. Okay. Now, finding and approximating and representing the observables and embedding the system in an invariance is still an important challenge in the application of Koopman theory. Now, there is this extended DMD. Like we said, knowing the phi case to be used, that means as the Eugen function, is still a problem. We have infinite number of them. Now, which are the ones that will give us good approximation of the Koopman's operator? Now, in extended DMD, an augmented state is usually constructed. So from nonlinear measurement GK. So in this case, we have a set of G1, G2, and let's say to GP. Now, this number P is selected to be much greater because we have said that the function space is supposed to be much greater than the state space, is much greater than the state space. So we have a Z at different times. We have, sorry, this is supposed to be Z. We have Z at T1, Z at T2 of these functions at T1, and then now that means the Z and all these G functions, they are to be determined by us. The user determines, and as we have to determine what G1 is, G2, and what each one of them is. So the number P is selected to be much greater than N. And then we also, just like we do in normal DMD, we have this. We have the columns of the measurements, and then this is the shifted version of Z. But in this one, we add ZTM plus 1. Now, as in DMD, a best fit linear operator AZ is computed, just like we did for this is just like applying DMD straight on the outputs of the measurements on the outputs. Oh, okay. Okay. I believe I've not so much. Now the extended DMD. Now with this under the extended DMD, we can actually use this one, because each one of the measurements can actually be written as a linear combination of some Eugen functions in the observable space. So we can write this as a linear combination, each one of these as linear combination of those functions in the observable space. So in the extended DMD, it gives room for us to determine kind of a little bit flexible, so that we can have very good approximation and actually select the Eugen function. In some cases, we can have some of them will be X, the state itself, the one X, and some of them are power polynomial function of the state. Some of them are transcendental function, sine, and we can, this allows us to do a lot with the approximation. And then we can come here and determine, we can do the minimization and solve for AZ. And that would be a good approximation of our Koopman's approximation. Koopman's operator, approximation of the Koopman's operator. Now, I want to conclude by, I think I don't know, but I want to conclude by saying that DMD is purely data-driven and is highly extensible. However, there are still open questions on how to choose the observable such that observable such, and to know how it affects the spectrum, and to also look at how the properties about the nonlinear dynamic carry into determination of the Koopman operator that we are going to use. Thank you very much for listening. I don't know if there are questions. Thank you very much.
Yeah, Thank you very much, Dr. Jibril, for that wonderful presentation. I suspect that at some point or the other, one or two of our listeners might have been stumped trying to follow. But that's actually the beautiful part about this presentation. It's a kind of seminar we actually look forward to having where everything isn't obvious at first glance, where you actually have to follow and actually have to think and expand your perspectives. So thank you very much once again, Dr. Jibril. We'll take questions now. If you have questions, you can either indicate by raising up your hand or just grabbing the mic and asking straight.
Just wait first, please.
Or comments, really, because this is a conversation. It's for most of us, this is the first time we are really encountering a treatment of the topic. So it's more of a conversation, I believe, rather than just
Yes.
Okay. Can I sort of make a comment?
Yes, sir.
Okay. Dr. Jibril, thank you very much for this talk and all the efforts put into making these slides together and then on the presentation itself. Just a few observations and probably comments I might want to make. If I can just summarize in some kind of sense my understanding of the Koopman operator. So we start off with a nonlinear system.
Yes.
And then we try to sort of find a means of projecting this into some kind of, we first of all do a kind of representation, which takes us into an infinite dimensional space in terms of the way we linearize it. Now that infinite dimensional space, we believe that we can find an embedding, a subspace in there that gives us a representation of the original system. So we stop there, and then we say, okay, there are different techniques we can use to sort of realize this kind of a system. So you talk about the DMD, whereby you essentially you did a kind of almost as if you do a principal component analysis. Say, okay, look, if I want to do an embedding, what's the best basis, a subset of bases I can use to represent the infinite dimensional space. So that when you did the eigen decomposition. Now that is then followed by a Fourier decomposition again. Now my question there is that you mentioned something that caught my attention when you said we have got a situation whereby we have got almost like a time and space representation. So you do the SVD decomposition first to capture some parts of it, and then the Fourier transform to capture the second part. So my suggestion, or should I say my question is, that SVD itself, supposing we have a kind of a multi-resolution version of that, would that have sort of obviated the need for the Fourier transform, for example? So that means the SVD itself has got inside it a kind of a time frequency analysis at the same time.
Yes, sir.
Would that be the case?
If I get the questions very well, sir. The SVD decomposition of Koopman of DMD decomposition actually does the two at the same time. It does.
Okay, you did mention that. You said that in terms of the two, the left and right eigen.
Yes, sir.
Yeah,
the U and the V. Yes, sir.
Yes, exactly. You mentioned that. So what is the purpose of the Fourier analysis then?
No, actually, the time. Okay, let me just go back here. Okay, sorry, I'm trying to. Okay.
Yeah, there.
Listen. So actually, this captures the spatial information about the signal, and then this file, which like I said during the presentation, that we are looking at discrete time system. So this is supposed to be the Eugen values here is actually the exponential function. When you do sampling, this lambda here is actually equals to this. So when you substitute back that here, this this information is actually from V. Sorry, from this V. Actually, this V are tells us about the time dynamics, how the thing is varying with time. So this
Okay.
yes, sir. This particular one kind of give us some things about the time dynamics, and this gives us the special information about the signal. So it's like it's giving us two things about this. This is direction, and this is about time dynamics in that direction. I don't know if
yeah, but the what you have here in terms of the phi, the phi itself,
yes, sir.
Those are the okay. Those okay. If you say the exponential functions there, yes, they represent some kind of basis functions, right? That's what they are.
These ones.
Yes.
No. Yeah. This is just like I'll say these are the basis function.
The phi.
Yes, sir. The phi, sir. These are the.
So the phi
like,
is a basis function.
Yes, sir.
And then the lambdas are the coefficients of the in those directions.
Yes, sir.
And the BJ is the Koopman coefficient.
Yes, yes, we call that is called Koopman's mode.
The Koopman mode.
Yes, sir. But it's actually the coefficients when we initially decompose any function into the basis function. So, sorry, sir. Let me quickly just show this. Now, initially, when you take any function and then you decompose it, I hope you are seeing my screen, sir.
Yeah.
Okay. So when take any function, a measurement, and you decompose it, a linear combination of these Eugen functions. And this is the coefficient. So this is supposed to be the Eugen function of that space in that.
So you've chosen P eigenfunctions that best represents the infinite dimension. That's what you've done.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. So
okay.
This is still this phi j.
That's the same phi, right? Right.
If we look at this as an exponential function with magnitude this along, something like that. So it's like this contains, so with time, because this is going to be, it's not going to be changing with time.
Yeah.
But with time, this will be changing with time. So this tells us about time dynamics of
Yes, okay. Okay, so then in this case then, so you have left off what we can call the spatial evolution then.
Yes, the spatial evolution will be captured by, we have a sum of this, sum of this one. So we have by this sum. So we have a set of them here, if I'm correct.
Yeah, okay, so what I'm struggling with now is that, okay, for example, say you when you do the SVD decomposition, you've got the U multiplied by the sigma. It will be a diagonal matrix of all the eigenvalues.
Yes, sir.
Yes.
Yes, sir.
Right.
Yes,
okay. And then you took V as the right eigen vectors.
Vectors. Yes, sir.
The right eigenvectors. U will be the left eigenvectors of the system. Yes. Now, what we have taken to use in this next set of equation are the components from V, right?
Yes, the components of V determines this. Determines
yes.
Yes.
Yeah.
Yes.
Yeah. Yeah. Okay. So what I'm just sort of trying to say that there's a component that you have not dealt with. That's what I'm trying to say. There's there's something left that this thing has not dealt with. Is it because it's not important, or is it because it's already been subsumed already? Because you said now that the phi, which is which is our basis function,
yes, sir,
essentially give us the spatial evolution, but no, it doesn't, because it doesn't change, because that is supposed to be fixed.
Yes, supposed to be fixed.
Yeah. Okay. I see. Yeah, actually, because the reason why I asked this question, I think there's a kind of vested interest here. I have to be honest with you. Is that when you mentioned the fact that it's as if the problem you want to solve on this page was a kind of a time frequency analysis of the system in a way. So I thought, why do it in 2 steps? You can do it in 1 step, because there is a multi-resolution version of the SVD that could probably solve it, that can do the two in one step. That's what I thought, but maybe that's not true. Okay, I see. Okay, all right.
Thank you, sir.
All right. Yeah, and the other question I have, I think it's on page 14. If I'm right, page 14. Is it page? No, it's cannot be page 14. This has escaped me in a way. Yeah. Okay. In fact, when you said right, when you mentioned the fact that it's going to be a data-driven, you did not go further in that part. Can you say a few more things on that? Yeah, data-driven approaches. What does this mean?
Okay. The data-driven approach here means that I hope you are hearing me. The data-driven.
Oh, of course, yes.
Okay. Yeah. Means that the operator can be computed. Can be determined from measurements.
Okay.
From measurement taking. For example, the DMD. For example, you want to approximate F. For example, if you have this particular one now, you have
right.
F that is nonlinear, and want to approximate F from measurements. And we know.
All right.
So we can approximate F by doing this least error fit. These are actually measurements of X at T1, T2, and like that. And this is also the shifted version of X, but we now add another column to make it of the same dimension. Then all these are data, and we approximate this matrix. We determine this matrix, which is an approximation to the nonlinear flow map F.
Okay. Now, okay, good. I like that. Now, can I raise two issues here?
Okay,
so, okay, if we say, for example, that this is a kind of system identification problem where you want to determine a system, right?
Yes, sir.
Now, if we also, because I want to sort of make a link between the idea of data-driven, it's a data-driven system identification problem. That's what it is, right?
Yes, sir.
So is it possible for us to then say, okay, supposing I have got, say, for example, say a regression problem.
Okay, sir.
Yeah, and it's a kind of nonlinear regression.
Okay.
Now, the issue here is for me to determine what is the function, that nonlinear function that regresses the features or whatever the state onto the target value, right?
Yes, sir.
Okay, so in a way, there's a link in a way between what you're doing, what you've just presented to us now, and say what happens in, say, machine learning, where you say you have got, because in essence in machine learning it's a kind of very complex system identification.
Yes,
you've got a set of weights in your network, your deep network, for example, right? Yes, we don't know the value of the weights. So yes, okay. Sir. Now we have data. We have some kind of way of training the data, using the data to train the weights. So we end up with some kind of a weight of some form. And we say, and when it settles, we say we now have an approximation of a function that is supposed to sort of map from the input to the output, right?
Yes, sir.
So is that kind of thinking wacky, or is it going in the right direction?
I think you are in the right direction, sir. Because actually, it's just we write a function that's we have a function. The deep network, we have a lot of them, and then
yes,
it's almost infinite in number, just like Koopman. And then we want to determine all those weights around. Weights in that. So we take different measurements for different data sample, and then we want to find those weights or determine those weights that gives us the best approximation
relationship
with the data. I think, sir.
Oh, fantastic.
I think so, sir. I think they are almost there.
Yeah. So then the last question now. Now, in the case of the way you have found A here, you use the Frobenius norm.
Yes.
Now,
Sir.
the Frobenius norm, the way we have it here, is supposed to give us some kind of restriction on the kind of A that we can find, right?
Yes, sir. Yes,
right.
Sir.
Is it possible for us to have said, rather than do that, we want to find the A that minimizes, say, for example, a different kind of norm. Say, for example, the infinite norm, or the L1 norm, or say the L0 norm.
Okay. Actually, sir, actually, since this is actually applied with regularization, it's some. Are you following what I'm saying, sir?
Oh yeah.
With
So you're saying that we will apply a regularization term to this one, right?
Term to this, so that we have just a few of, I mean to specify the
A.
The A, so that we have just.
I see.
Yes.
So it's like saying what you have here now would be admin A Frobenius norm of x bar prime, minus ax plus lambda, maybe
plus lambda
L1 norm of A. Or L0 norm of A, something like this nature, something like that,
maybe
right?
Nuclear norm of A, something like that, sir.
Oh, right. Okay. So and that is also considered normally, right?
Yes, sir. Yes, sir. Actually, in some in Cindy, there was one sparse identification by Broughton. Cindy, there's this there's this code they wrote for determining that, and they use sparsity inducing
norm. Okay, sparsity inducing norm. Yeah.
Yes, sir.
Okay.
Yes, sir. Yes.
Thank you very much. I really enjoyed the talk. Thank you so much. It's very nice.
Thank you very much.
It's very good. Yeah.
Thank you, sir.
So I'll release the floor. Please, more questions and more comments, please.
Thank you, sir.
Yes. My pleasure. My pleasure. It's very good. Thank you.
Thank you, sir.
Do we have any questions, comments? There seem to be no additional comments.
Okay, so
actually, just a quick comment on my part that okay, we have Dr. Awe. Okay, Dr. Awe, just a second, Dr. Awe. So a quick comment on my part is that additional reason to look at using Koopman is, I think it was Dick Hammond that suggested that if you want to do good work, you want to work in an area that is current. You want to work on a problem on a tool that is still very current. And I think it's interesting now. Mesic, I think, it's his group mainly driving this now, and maybe some collaborators. And from what I've seen, from a few YouTube clips I've watched, there's quite a lot of work to be done here. And of course, nonlinear problems are harder to work on, but they actually, there's a much richer set of dynamics you can actually play with nonlinear problems. Yeah. So I'm saying it's actually a very good time for us as a community to be looking at Koopman methods across the entire span of the problems we are looking at.
Yes.
So I'll invite Dr. Awena for his question or comment.
Thank you, sir.
Yeah, thank you very much, sir, for the presentation.
Thank you, sir.
I'm just wondering if it's possible, maybe in subsequent meeting, if we can spice this idea up with real world problem. Actually, that may, in a way, open up the mind of listeners and be able to draw parallel between the instances and what they may be working with. So if you can have a real world problem and we see how these procedures are applied towards deriving the solution, that may help the listener better to see the relevance of the concept to what they may be working on currently or maybe working on later. Thank you.
Okay, I want to apologize for making it so dry and well, I believe next presentation. Actually, the goal was to, if you look at the title, is to see how to apply it at different problems, and then
I will.
we also I also wanted to make some MATLAB write some code and then see what um, I'm talking about. For example, DMD, there are codes for that. And I also have a data which we can easily work on and to see how that is really done and achieved. But I'm sorry, at least for now, I'm sorry that is so dry. I believe you accept my apology.
Thank you, Dr.
Um,
Jibril. No apologies required.
Can I make a comment? I wanted to make a comment on Dr. Jibril's response to the question. Dr. Awe, thank you for the question you've raised. But I think also that question also raises another question. I have not worked on Koopman operator before. No, never. But there was something I used, and that is the fact that I have asked myself several questions about, I do machine learning. What is it all about? What is it all about? It's about function approximation.
Yes.
It's about determining we have a function that is very complex. We don't even know what the nature is. So we give it a kind of a form. That form could be some kind of something in some kind of hypothesis space. And we use data to find the best of those form of solution of approximation that best meets the concept we want to describe.
Mm.
So because I have that kind of understanding of machine learning in terms of what it's all about, it becomes easy for me when Dr. Jibril said, this is about nonlinear functions. He wants to sort of find a way to linearize it and then solve some kind of problem. So I could relate that to my problem straight away. And the only way I could do that, as I said, is because of this concept of saying, we must ask the question all the time. Anything we do, it doesn't matter. In fact, in some cases, applications will becloud our eyes in terms of things that are similar, we see them as being not similar because we're too worried about the application part. I'm not saying we shouldn't worry about applications. A lot of my work is applied. But we have to peel off the surface and go be beyond that application to say, what is it all about? What is it all about? And then we can see beyond the application, we can see similarities, we can pick ideas from other areas and use to solve our problem. So I'm not too sure various areas that all of us are working on in a way, but I will implore us, I will actually go as to say, I beg that please find time to write down a small note for yourself, 2 pages, 3 pages, what I'm working on, what is it all about? What is the essence of it? Because once we get to that point, believe me, we will have a lot of tools to use in a way. Because, for example, this talk today, I'm beginning to think to myself, in fact, there's several things I thought about straight away. When he said, oh, this and this and this, because I have worked in some areas of SVD, looking at SVD from a multi resolution point of view, I quickly said, wow, can my method be used in what he's trying to do? That was why I asked the initial question, that can we sort of, instead of 2 steps, can we just use 1 step? So, okay, my understanding was not correct. He corrected me, that's fine. But I was able to link that straight away by asking the question, what is this all about? Is it about time frequency analysis? Yes, if it's about that, we have a solution for that. It's about this. Can we apply that? So I think the talk I gave when we started this whole seminar series was to point us in that direction, that we need to go beyond the application of our area. We need to go and ask the question, what's the essence? What is it all about? In fact, I use a very dirty word. I say, what the heck is going on here? What the heck is going on here? And once we get that, that's it. I give an example. If you have noticed, recently people are talking about attention networks in machine learning, attention networks. Then my students say, I don't understand. I said, the question you should ask it, why do you need attention? What is it for? Where does it come from? We look at the whole thing. It turns out to be a kind of correlator. It's a correlator. That's it. It's a very fancy way of saying correlator. So it's a correlation function. I say, in how many ways can we do correlation? You can do correlation by doing straight correlation, or you can you can dilute it and use even just convolution to do the same thing. And in fact, when we say convolutional neural network, it's nothing more than a kind of really correlation neural network, because they're not doing convolution at all. Because convolution means that you take one signal, you invert it and rub it against the other one. In neural network, we don't do any inversion. We just rub signal against each other, which is correlation in a way. So by asking that kind of question, because we've done a lot of basic things. I mean, we know about correlation, we know about Fourier transform, we know about all these little things here and there. And they're still the basis of everything that everyone does at the end of the day. Believe me, there's no magic. So the answer to your question would be, maybe I will have asked the question in a slightly different way. I'll say, the problem I'm trying to solve is this. How does it apply to it? Let's explore it together as in a kind of a conversation. And that will be maybe another 2 hours of talk for us to explore things before we finish. So let us try and say, let's bring our problem to this forum and say, okay, you've talked about this X, Y, Z. I'm solving this kind of problem. I think the essence of my problem is this. And how can you see a relationship between that essence and this one? Because it's at that level that we see similarities, not at the application level. Application level, we don't see similarities anymore. It's beclouded. And if we want to get deep understanding, I think we have to go down to that level where the application is hidden for a while, and we look at the essence of things. And then we see, they're the same thing in a way. I mean, to put it in a very funny way, it's like, say, a Muslim and a Christian are bickering about the way they pray to God in a way. But when they go down to the basics and say it's about praying to God, so the application, your doctrine here and there, is immaterial at the end of the day. You just pray to God. And is there a third way of praying to God? Yes, there's a third way. Is there a fourth way? There's a fourth way. So we begin to write papers. We begin to sort of create new religions, if we like, so to speak. And we write more papers, more theories in a way. So that's how I see the way I will have approached that. The way I will answer the question you posed, Dr. Awe. Thank you very much.
Thank you, sir. Thank you very much, sir.
Thank you very much, Prof. Mr. Kologumba.
Yeah, thank you. I don't know if you can hear me.
Yeah, I hear you.
Okay, great presentation. A little bit of also some suggestion on perhaps a bit of comparison of the effectiveness of the Koopman method with maybe one of the more conventional system identification techniques, just to show its powers and to show that not only theoretically is it sound, it also can yield some graphs, some correlation plots and so on that make it very powerful compared to what already exists and so on. So that's just a bit of a suggestion on that one, but I'll go back to this issue also of the practical versus the theoretical, the perennial matter of, or the perennial criticism perhaps of things that are mathematical, perhaps control, perhaps system identification. My view on that has always been that we must find a way to be comfortable both in the abstract and the practical. My argument has always been that you can represent a practical system or a set of practical systems with abstraction. On the other hand, you can also create practicality from abstraction. You do not have to always have a physical system that you characterize with models. You can use an idea of a model or how things should work to create physical systems that will solve specific problems. And my argument has always been that if something is very heavy on math, well, it is a description. It's like calling something names. A name can be general, it can be specific. But we must be comfortable in both worlds to be able to address problems of a very deep technical nature. And in some conversations, we will go deep into technical stuff, while, as Prof. Ogunbono said, trying to address the essence, ultimately, of perhaps dealing with instability in a general sense. People see abstraction as a negative. I see it as a positive, because with abstraction, you can create many more things. You are addressing an abstraction to address maybe 1,000 possible existing or yet to exist systems. I talk about the Kalman filter as an example. I mean, Kalman filtering is abstraction, but the number of places that Kalman filtering has entered in the biological, in the physical, in the chemical is astounding. Meanwhile, the person that proposed it just thought, well, this filter can do something to filter out noise and to do some advanced estimation in a pack of systems. Your system doesn't have to already exist. You don't even need to know what it is. I will use Lyapunov also as an example, and I think Lyapunov has featured a lot even in data-driven systems, neural networks, and so on. Lyapunov wrote his PhD thesis in 1892. In that, he proposed his methods, the famous first and second methods. He died in 1918. It was in the Second World War that Lyapunov really became popular after his death. And it was because, well, in this quest for automatic gunships and all kinds of things in an attempt to win the Second World War, there was the need to analyze this new brand of nonlinear systems that were being created. And then something that had not been, something that was just newly created needed a tool that had been created by someone who was already dead, probably up to 30 years before. My point is, that's the power of abstraction, the ability to be able to even solve problems that don't yet exist. It's the longevity of abstraction is amazing. So as much as it's important to have practical, physical, existing demonstrations, I can decide, like I did about 2 years ago, to just sit down in my house and create a system that I feel will solve problems just by writing out equations. And with that, I can come out and, test that system that may not even exist, control that system that may not even exist. And then many years into the future, when we get more advanced technologies, like we are doing, guess what, with Koopman, 1932. This is 2021, almost 100 years later. And because it is good abstraction, it doesn't have to be physical. That's my own take. And of course, we are free to disagree, but I believe abstraction is not a vice, it's a virtue of engineering, and we should embrace, even as we seek to make the idea of what we are doing to be as appealing as possible using all the physical aids that are in existence. So that's my contribution.
Thank you, sir.
Thank you very much, Mr. Ogumba. I don't think Dr. West's question was actually challenging the importance of abstraction. I think it's more a question of, anyway, first, I think all of us here would agree that abstraction is very important. And I don't think anybody, not even Dr. West, would question its importance. I think his question was more about the practical issue that when you encounter a topic for the very first time, ideally, as Professor Ogunbono said, ideally you would understand your work or have something that is easy to link to that topic that you're just encountering. But perchance you don't have that luxury, or that at that particular instance, you can't make that link. I think his point was that it sometimes helps if, as it's been presented, there are more case studies, examples, if you will, that opens tendrils that allows you to link that new topic you're just encountering to your own work. I think that's the point he was making. It wasn't about challenging the importance of abstraction. And Mr. Akimbabwe.
So, good afternoon, everybody. Good afternoon, sirs and mans. Yeah, thank you, sir, for the presentation. Great presentation. Mine is just a comment or something maybe for us to consider. I've always thought that the connection, or there should be a connection between, or we should find a way to link Koopman's operator to what's called deep learning in a way, because right now everybody is talking about, I mean, quite a lot of people are talking about explainable AI or explainable data, what's called deep learning, in the sense that what deep learning gives to us, we are not able to make sense of it. I mean, the hidden things. All right, but with Koopman, what we read about recently says something like you can explain. Dr. Jubilee mentioned Koopman modes and all that, or the Higgs functions and all that. The Higgs functions of Koopman are quite physical in a way. When you see those modes, you can see what they are physically. You can explain them physically. Now, my question is, can we link it up to and since Koopman has, you know, there's a link between Koopman really and what's called AI, deep learning. Can we really, or how should I put it now? Can it really perform the explainability in a way of deep learning? Can it function in that space? Thank you, sir.
Okay, thank you, sir. Thank you for the question. Okay, just like you have said, and Prof has also said the other time, that we can, in all this regression or approximation we are trying to do, we are trying to express a particular model, or a particular, we are trying to fit a model to our data, and it's boils down to finding some kind of coefficient in a particular space. Even with deep learning, it's still, you have a space of maybe radial basis, you have some functions that have been defined, and then you want to find the coefficients. Now, so we have very complex one, but with Koopman, you actually can be very expressible. But I like I said the other time, the problem with Koopman is problem of knowing what and which agent function to consider. But there is a particular paper on determining or deciding which agent function to be considered for a particular case. And what they do, they use autoencoder a deep learning autoencoder to actually help in determining the function, the agent function of the system, so that you can select optimally, very good agent function for a particular problem. So by that means you can actually decide, the interpretability that is in Koopman can be brought out using the deep learning also to actually select the function that best approximates or interprets our problem very well. I don't know if I'm making sense.
Can I make a comment on that?
Okay, sir.
Yeah, actually, if you sort of look at the issue of eigen decomposition or even the principal component analysis or the kernel version of it, the nonlinear version of it, which is kernel PCA or kernel SVD, but it's a projection onto a kind of a subspace. It's a subspace problem or manifold learning problem. Unfortunately, when you end up with a manifold, oftentimes, in fact, most of the time, it has no bearing anymore with the original space in terms of interpretability. Because, say, for example, if I say I take a data set, for example, and I do a singular value decomposition on it. Now, what I'm trying to look for is some kind of I'm looking for some principal axis along which I can project the data to be able to sort of maximize the energy compaction in a way. Now, if those so-called if the eigenvalues are ordered, and I pick the top in terms of ordered in terms of, say, ascending order of, say, descending order of magnitude, if I retain the top k eigenvectors corresponding to the top values, I'm sure to have retained the best possible energy compaction of that, or representation of that signal.
Yes.
However, that new eigenvectors I have, yes, they may have some kind of oscillations in a way that sort of says that there might be some kind of harmonic decomposition in some sense, but they do not have the same, they do not have any relationship anymore. Well, they have a relationship, but it's a kind of complex relationship they have with the original space from which I have projected. So we have lost, also in that case, the interpretability. Say, for example, let's just say, take a simple example. I'll say, okay, I'm going to sort of typify a human being. I'll measure the size of the cap they wear. I'll measure the size of the shirt they wear, the shoe size. I'll measure their weight, the body mass index, or the fat content, all of this kind of thing. Those are things that are physically known, right?
Yes.
I measure these for, say, many say the whole of if a city, for example. I did that. Now, when I did that, suppose that I say, okay, I'm going to now go from that fat content of the body mass index. Let's say, supposing that number of features or measurements happen to be, say, 30 that I took. And I said, okay, look, I don't have the luxury of using 30 measurements per person. I want to limit it to, say, only 15. The tool we have, the tool we know, is to do a kind of a principal component analysis or SVD, that type, eigen decomposition type of stuff, right? Yes. And pick the best way to represent it. Yes. In fact, the autoencoder is known to be doing the same thing. It's a kind of subspace analysis, because when you go through your from the data set, you go through a bottleneck, right? You go to the bottleneck and then you expand back. In that bottleneck, what you have there is the subspace projection, because you have got n inputs. In the bottleneck, you have maybe k where k is much less than n. But now what you get here, that representation, while it is very economical and also representative, it does not translate into whatever. It could be simply say, take one of my heart, the 1/4 of my heart size, 2/3 of my shirt size, 1.5 of my shoe size, and that becomes one new feature in a way. Why does it do that? We don't know. So that unknown is still there. Yes, that unknown is still there. We still have that problem. So I'm not too sure that problem is going to go away anytime soon. The only way it can go away is to say, okay, if we go back and look at the way in which each feature, say the eigenvectors in each of the new space, how they're made up, and we say, okay, let's go back and try to explain this. This is actually putting together things about fat in the body. Oh, this one is actually putting things about height of the person. Oh, this is equivalent to the maybe some other kind of property of the person. We can go back and do that. Then we have explanation. But as it is in itself, no, it has jumbled everything together somehow. And even more so if it becomes a nonlinear case, whereby it might be something squared of the heart size, plus a quarter or cubed of the shoe size, put them together. Yeah. No, it is true. We've tried to analyze it this way before, and we found that we said, so what does this mean? And that's why this non-explainability problem comes in. So it really is said again in eigen decomposition problem. It will not go away. I don't think that Koopman will necessarily solve that problem.
Yeah, thank you very much, Prof.
Thank you, sir.
I think clearly this is a conversation that just has to continue. And, and really our goal, our aspiration here is to have a community of researchers using Koopman tools, developing Koopman operator theoretic tools. And really there are very few of such communities globally. So if we can do this, it actually will do a lot to give us more, give our work here more exposure. Hopefully we can grow both depth-wise and, depth-wise, the theoretical treatment as proposed or exposed by Professor Gumbono, and also breadth-wise in terms of the application areas as exposed or suggested by Dr. Awe. I think there's room to grow in both directions, and I'm confident.
Indeed, of course.
We'll grow in both directions. I'm actually hoping that soon we can have another session, a more tutorial-like session where we consider computational tools for Koopman operator theoretic methods. I hope we can put that together sometime soon.
That would be very good. Yeah.
Yeah, just to stimulate the growth of this community.
Yes.
So
can I just make a comment before we finish? My comment in terms of Dr. Awe's question and the response from Dr. Jubril was not to say that we shouldn't look at both. What I was trying to say, I just want to use the opportunity to say there's a chance for us here to dig deeper into the essence of our work, because it is at that point we see similarities. It is at that point when we begin to see opportunity for collaboration. At the application level, it's not easy to see similarities because that application has got its own nuances and it beclouds the essence of the problem, the essence of the things that we are trying to do. So I'm just trying to exhort us to say, while we need to look at the application, let us not forget that to engender collaboration is at the level of that essence that it becomes possible. And that's why I use the analogy of religion to say, if we go down, there's no reason why we cannot see that probably all religions are the same in a way. They are trying to split to some being outside themselves in some ways, right? So so please, I don't want that what I said to be misconstrued as saying that application is not important. It is important.
No. Oh, sure. I didn't misconstrue you, so I actually understand. I got your point very clearly, sir. I wasn't, and in fact, I would go as far as to say that I believe that it's more important to dig depth-wise first before breadth-wise. So I definitely am in tune with what you were saying, sir. I agree absolutely.
Thank you. Thank you.
Thank you, sir. I noticed the name on the attendance list. I've not been in the same room with this individual for I think over 10 years now, even if this room is virtual. Dr. Ambrose Adibgege is, you probably want to say one or two words. He's in the US. And this actually is an opportunity for me to observe that this meeting currently spans 15 time zones. We have people in the US, we have people in Australia. So Dr. Adibgege, it's a pleasure to have you with us. Do you want to say one or two words?
Fantastic.
Thank you very much, sir. Thank you. Actually, I would have, the time for the presentation I was still sleeping. I joined towards the end, and I think what I've heard is really interesting. And, and also opportunity to listen to Dr. Jubril. It's been quite a while.
Good afternoon,
and also
sir.
to see the face of Dr. Ayodele. I think maybe your subsequent presentation, I will be able to at least listen fully into what you're doing. But it's very impressive. Thank you very much.
Thank you very much, Dr. Adibgege. And
which part of the US are you, Dr. Adibgege? Please, can you tell us?
I'm in New Jersey.
Oh, in New Jersey. Okay, upstate. Yeah. All right. Yeah. Oh, fantastic. Yeah. Thank you for attending this. We really appreciate it. This is very good. And maybe at some stage in the near future, you might also consider to give us a talk on a kind of tutorial nature talk on something that of interest to you.
Okay. Noted,
Yeah.
sir.
So, Dr. Aligbega, we also appreciate if you bring your colleagues to attend our meetings anytime you are joining us.
Oh, okay.
Our goal is to totally eliminate the gradient between working in Nigeria and working abroad. We want to operate to be distinguishable from a department in North America or Australia or the UK. So we want to have as much involvement of researchers from the US, UK, Australia as possible.
That's beautiful.
Thank you.
Okay, thank
Yes.
you,
Do we have any additional comments or questions? Okay, we're wrapping up now. We've spent 2 hours, so I think it's time to appreciate all our participants. We're very grateful. I kept keeping at the attendance list, and really we had a full house to the end of Dr. Jibril's presentation, and I thought that was actually very, very impressive. And I want to say thank you to all of you for joining us. There are quite a number of names here that are not actually members of the OE community. I'm sorry I can't mention names individually. I just want to say thank you to all of you for joining us, and I hope you join us for the next seminar. We aim to have a seminar every month, either first or last Wednesday of the month. It's still in a state of flux now, but we'll settle on one very soon. But I have no doubt that we'll let you know when the next seminar comes up and that you join us. Thank you very much, everybody. Have a nice day.